Have you ever looked at a triangle and wondered, how much space is inside that shape? Well, you're in luck. There is a super clever way to find out, and you don't even need to know any of the angles. All you need are the lengths of the three sides. This is where a fantastic piece of mathematics comes into play, known as Heron's formula. It's like a secret key that unlocks the area of any triangle, no matter its shape or size. Whether it's a long, skinny triangle or a perfectly balanced one, this formula works every single time, which is pretty cool if you ask me. It's a powerful tool for anyone who loves shapes and numbers. So, what is this amazing formula? Let's break it down. First, we need something called the semi-perimeter. That sounds complicated, but it's not. The perimeter is the total length around a shape. So, for a triangle with sides we call A, B, and C, the perimeter is just a plus B plus C. The semi-perimeter is simply half of that. We use the letter S to stand for the semi-perimeter. So the first step is to calculate S equals the sum of A, B, and C divided by 2. Once you have S, you're ready for the main event. Heron's formula for the area, which we'll call A, is A equals the square root of S times S minus A times S minus B times S minus C. It might look a bit scary with the square root symbol, but it's just a few simple steps of multiplying and subtracting. Let's try an example together. Science is all about trying things out. Imagine we have a triangle with sides that are 5 centimeters, 6 centimeters, and 7 centimeters long. So A is 5, B is 6, and C is 7. First, let's find our semi-perimeter S. We add the sides together. 5 plus 6 plus 7 equals 18. Then we divide by 2. 18 divided by 2 equals 9, so our S is 9. Now we can plug everything into the big formula. We need to calculate S minus A, S minus B, and S minus C. That's 9 minus 5 equals 4, 9 minus 6 equals 3, and 9 minus 7 equals 2. Now let's multiply all those numbers with 9 times 4 times 3 times 2. This gives us 216. The final step is to find the square root of 216, which is about 14.7. So, the area of our triangle is about 14.7 square centimeters. See, you did it! Now there is one important rule to remember, the triangle inequality theorem. This is a fancy way of saying that, for any triangle to exist, the sum of the lengths of any two sides must be greater than the length of the third side. For instance, you can't have a triangle with sides of 2, 3, and 10. Why? Because if you try to connect them, the two shorter sides wouldn't be long enough to meet. Heron's formula knows this. If you try to use numbers that break this rule, the formula will give you an impossible answer, like trying to find the square root of a negative number. It's a built-in safety check, which is another reason why it's such a brilliant piece of mathematics. So, who was the genius behind this formula? His name was Heron of Alexandria, sometimes called Hero. He was a Greek mathematician and engineer who lived a very long time ago, around the 1st century AD, in the amazing city of Alexandria in Egypt. Alexandria was a bustling center for knowledge, home to a great library and brilliant minds. Heron was one of them. He wasn't just a thinker, he was a doer. He wrote about all sorts of incredible inventions, like the first steam engine called an eolipile, automatic doors for temples, and even a vending machine that dispensed holy water. He was truly an innovator, someone who used science and maths to solve real-world problems. Heron wrote a famous book called Metrica, and it's in this book that we find the first known written proof of his formula. He laid out the steps very carefully, showing everyone how to calculate the area of a triangle using only its sides. But here's an interesting twist. Some historians believe the formula might have been discovered even earlier. There's some evidence that the great Archimedes, who lived a few centuries before Heron, may have known about it. It's possible that Heron was the one who brilliantly wrote it down, explained it, and preserved it for all of us to use centuries later, which is a massive contribution to science and engineering. How did mathematicians prove this formula is correct? The proof is quite elegant. One common way uses some basic geometry and algebra. It starts with the standard formula for a triangle's area equals 1/2 times base times height. Then, using the Pythagorean theorem, a squared plus b squared equals c squared for a right-angled triangle, and some clever algebraic manipulation, you can express the height of the triangle using only the lengths of the sides A, B, and C. It's a bit like a puzzle, where you substitute one piece of information for another until you are left with just the sides. It's a beautiful demonstration of how different parts of mathematics are all connected. While Heron lived in Egypt, similar ideas were popping up in other parts of the world. Mathematicians in ancient China, for example, also developed a similar formula. In the book, Mathematical Treatise in 9 sections, written by Qin Jushao in the 13th century, a method for finding the area of a triangle from its sides is described. It shows that great ideas can often appear in different places when people are trying to solve similar problems. It's a testament to human curiosity and our shared desire to understand the world around us through the universal language of mathematics. Consider the world connected by numbers. You might be thinking, this is neat, but do people actually use this in real life? Absolutely. Heron's formula is incredibly useful, especially when you can't easily measure the height of a triangle. Think about a land surveyor. They might be measuring a triangular plot of land on a hillside. It would be very difficult, maybe even impossible, to drop a measuring line straight down from the highest point to find the height. But measuring the 3 sides along the ground is much easier. Once they have those 3 lengths, they can pop them into Heron's formula and calculate the exact area of the land. This is vital for creating maps, defining property boundaries, and planning construction projects. Architects and engineers also find Heron's formula to be a trusty tool in their kit. Imagine designing a modern building with interesting triangular panels on its roof or walls. To order the right amount of material, whether it's glass, steel, or concrete, they need to know the exact area of each of those panels. Since they design these shapes on a computer, they know the lengths of all the sides. Heron's formula allows them to calculate the surface area of complex, angled structures without needing to know a single angle. This helps them make their designs efficient, reducing waste and saving money. It's practical maths in action. The formula is also a cornerstone in computer graphics and video game design. When creating a 3-dimensional model of a character or an environment, artists build everything out of thousands or even millions of tiny triangles. These triangles are called polygons. The computer needs to calculate the surface area of these shapes for many reasons, like applying textures, the skin of the object, correctly, or figuring out how light should bounce off the surface. Heron's formula provides a fast and reliable way for the computer to get the area of every single one of those little triangles using only the coordinates of their corners. Let's not forget about art and design. An artist creating a large mosaic or a stained glass window might design a pattern made of many different triangular pieces. To figure out how much colored glass or tile they need for each section, they could use Heron's formula. If they know the dimensions of each triangular piece in their design, they can calculate the area and ensure they have enough material to complete their masterpiece. From mapping our world to building our cities and creating digital universes, this ancient formula is still hard at work behind the scenes. One of the most fascinating things related to this topic is something called a Heronian triangle. This is a special kind of triangle that has a wonderful property. All 3 of its side lengths are whole numbers or integers, and its area is also a whole number. Our earlier example with sides 5, 6, and 7 gave us an area of about 14.7, which is not a whole number. But consider a triangle with sides 13, 14, and 15. Its semi-perimeter is 13 plus 14 plus 15, divided by 2, which is 21. When you use Heron's formula, you get an area of exactly 84. Since 13, 14, 15, and 84 are all integers, this is a Heronian triangle. Finding these special triangles is a fun mathematical puzzle. So, why does Heron's formula remain so important today? Because it represents a fundamental idea in science and mathematics: simplicity and power. It shows us that we can find out something very important about a shape, its area, with very simple information. We don't need fancy protractors to measure angles or complicated equipment to find heights. All we need is a ruler or a tape measure. This makes it accessible to everyone, from a student in a classroom to a professional surveyor in the field. It's a beautiful example of how elegant mathematical rules can make complex problems much, much simpler. The formula teaches us a valuable lesson about looking for different ways to solve a problem. When one method, like finding the height, is difficult, there is often another, more creative path to the answer. Heron's formula is that creative path for triangles. It encourages us to think outside the box and use the information we have, rather than being stuck by the information we lack. This way of thinking is at the heart of all scientific discovery and innovation. It's about being resourceful, clever, and persistent in our quest for knowledge. In the end, Heron's formula is more than just a dusty equation from an old book. It's a bridge connecting the geometry of the ancient world to the technology of our modern one. It's a practical tool that helps us build, design, and explore. And it's a reminder that even the simplest shapes around us hold fascinating secrets, just waiting to be unlocked by the power of numbers. So the next time you see a triangle, remember Heron and his amazing formula. You have the power to discover what's inside. Science is all around us.